You know that feeling when you're starting to code something new and you type in print, "Hello world."
Oh, yeah, absolutely.
You
That
know,
first little check.
it's that first step, right? Just making sure everything's working. You've got the basics
Oh,
down.
exactly. Well, there's kind of a similar thing in quantum computing, a hello world, if you will.
And that's what we're diving into today using Qiskit, specifically Qiskit 1.x.
That's the plan. We're going to unpack the sort of fundamental workflow, drawing from a really good Qiskit YouTube video.
Ah, the Coding with Qiskit 1.x series, episode 3, I think, with Derek Wong.
That's the one, hello world. It's a great source for understanding how you actually start programming these quantum computers. Think of this as, your shortcut to getting up to speed.
Okay, so our mission for this deep dive, break down the essential steps. We'll start with a simple example.
A 2-qubit Bell state
Yep, a classic. And then we'll see how those same ideas scale up, like way up.
to a 100-qubit GHZ state. Wow. So we're not just looking at code, we want the concepts behind it. Precisely. And Qiskit actually gives us a nice structure for this. They're patterns for quantum workflows.
Right, I remember reading about those. There are 4 steps.
4 main stages, yeah. First, you map your problem onto quantum circuits and operators. Figure out how to ask the quantum computer the question.
Okay, map the problem, step 1.
Step 2 is optimizing that circuit, making it runnable, efficient, especially for real hardware.
Makes sense? Then step 3.
Execution, running it, either on a simulator or, the actual quantum hardware.
And finally, step 4, getting the answers back.
Post-processing, exactly, analyzing the results. So we'll follow these 4 steps for both the 2-qubit and the 100-qubit cases.
Perfect. Let's start with step 1 then, mapping the problem for that 2-qubit Bell state. What is a Bell state exactly?
Ah, good question. It's a really fundamental state in quantum mechanics. It involves 2 qubits, and they become entangled.
Entangled, meaning linked together in some weird quantum way.
That's a good way to put it. They're in a superposition, sort of 0 and 1 at the same time, but linked. It's specifically the state where they're either both 0 or both 1, written like 0, 0 plus 11.
Okay, 0, 0 plus 11. How do we actually make that happen in Qiskit?
So the video shows this clearly. You start with Qiskit's quantum circuit object. Pretty standard.
You tell it you want 2 qubits.
Right, quantum circuit 2. Then the magic happens with 2 quantum gates. First, a Hadamard gate.
The H gate.
Yep, the H gate. You apply that to the first qubit, which is qubit 0 in programming terms.
That puts it into superposition, like that quantum coin flip idea.
Exactly. It's now kind of 0 and 1 simultaneously. Then comes the second gate, a CNOT gate.
CNOT, or CX. That one needs 2 qubits.
It does. A control and a target. If the control qubit is 1, it flips the target qubit.
Okay.
And because our first qubit is in that superposition state from the Hadamard gate, this CNOT gate creates the entanglement. It links them.
So the H gate creates the maybe, and the CNOT creates the linked maybe.
Hey, yeah, something like that. It results in that Bell state, 0, 0 plus 11, where their outcomes are correlated. It's a purely quantum thing, this entanglement. No classical equivalent.
And the video showed you can actually draw the circuit. See the H and the CNOT.
Yeah, circuit.draw. It's super helpful for visualizing what your code is actually building. You see the H on qubit 0, then the line connecting 0 and 1 for the CNOT.
Okay, so we've built the circuit. But step 1 is mapping to circuits and operators. How do we check we actually made a Bell state?
Right, good point. We need to measure things. And in quantum, we talk about measuring operators and finding their expectation values.
Expectation values. Like the average result, if you ran it tons of times.
Basically, yeah. For a Bell state, theory tells us certain 2-qubit operators, specifically ZZ and XX, should have non-zero expectation values. That's a big sign of entanglement.
ZZ and XX, meaning applying a Z-gate measurement to both, or an X-gate measurement to both.
Kind of. It's measuring the correlation in the Z basis and the X basis. But then single qubit operators like ZI or IX.
Where I is just identity, like doing nothing.
Exactly. ZI means Z on the first qubit, identity on the second, IX is the other way around. Those, along with XI, should have expectation values really close to 0 for a proper Bell state.
So these operators are like our measurement tools, our probes. How do we define them in Qiskit?
Qiskit has a class for this, polisum. You import it from qiskit.quantuminfo.
Polisum up. Got it.
And then you can create them pretty easily just using strings, like literally the strings ZZ for the ZZ operator.
Oh, nice. So ZIXXXXXI.
Yep, just like that. The video shows creating these and sticking them in a list, ready for later.
Okay, step 1 complete. Map the Bell state problem to a circuit and the ZZ, XX, ZI, XI, IX operators.
Yeah.
Now, step 2, optimization.
Right. Now, optimization or transpilation is usually super important for real hardware, dealing with qubit connectivity, which gates are native.
Translating our ideal circuit to what the machine can actually run.
Exactly. But for this first example, the video uses the local air simulator.
Ah, the software simulator running on your own computer.
Right. And because it's a simulator, it's flexible. It can handle this simple 2-qubit circuit directly. So for this specific case, we actually skip step 2. No optimization needed.
Convenient. So straight to step 3, execution. Running the circuit on this air simulator. How's that done?
This involves using something called an estimator primitive. It's designed specifically for, estimating those expectation values we talked about.
Okay, an estimator. Where does that come from?
From Qiskit.primitives. And the video actually shows a common little hiccup here.
Oh, what happened?
A module not founder. The Qiskit package wasn't installed yet in that environment.
Ah, the classic forgot to pip install moment. Happens to everyone.
Totally. So Derek, the presenter, shows the fix, activate the environment, pip install Qiskit. Simple enough.
But then there's that crucial extra step.
Restarting the kernel. Yes, if you're in a Jupyter notebook or similar, you have to restart it after installing so it actually sees the new package.
Good reminder. Okay, so Qiskit is installed, kernel restarted. Now we can use the estimator.
Yep. You create an instance of it. Then you call its run function.
And what do you pass into run?
The quantum circuit we made and that list of operators, ZZ, ZI, etc.
Okay. Circuit operators. Makes sense.
There's a small note in the video about this specific version of the estimator, though. It needed the same number of circuits as observables.
Oh, really? So if you have 5 operators, you need to pass the circuit in 5 times?
Kind of, yeah, or structure it that way. It's a bit awkward. They mentioned the newer V2 primitives are much smoother in that regard.
Good to know. But they make it work here. And since it's a local simulator, the results are fast.
Instantaneous, pretty much. No waiting in a queue for hardware access. You get the job object back right away with the results.
Nice. Okay, execution done. That leaves step 4, post-processing and plotting. What do the results look like?
Well, the estimator actually does a lot of the heavy lifting in terms of calculating expectation values. So the post-processing is mainly about visualization.
Making a graph.
Exactly. Using matplotlib.pyplot, the standard Python plotting library, they set up labels for the x-axis corresponding to our operators, ZZ, ZI, XXZI, IX.
And the y-axis is the expectation values from the results.
Precisely. They extract those values from the job results. Then they just plot points, operator name on the x, expectation value on the y.
Yeah. Does it look like a Bell state?
It does. The plot clearly shows the expectation values for ZZ and XX are really close to 1.
Which is the sign of entanglement we wanted.
Right. And conversely, the values for ZI and XI and IX are all very close to 0. It's like the theory predicts.
Perfect. Any small errors?
Tiny deviations, yeah. The video mentions this is likely due to simulated shot noise, the statistical noise you'd get from a finite number of runs, even on a perfect device. It mimics reality. Okay,
so a successful hello world. We made a Bell state, measured it, confirmed it. Qiskit works.
Exactly. But then the video takes a big leap.
To the 100-qubit GHZ state, scaling up dramatically.
Right. And the cool thing is seeing how that same 4-step workflow still applies, just with more complexity.
So what is a GHZ state? Greenberger-Horn-Zeilinger.
That's the one. Think of it as the big sibling of the Bell state. Bell was 0, 0 plus 11. An n-qubit GHZ state is 0.0 plus 11.1.
So all zeros are all ones across all n-qubits.
Yeah.
Entangled across the whole system.
Exactly. Maximum entanglement across many qubits. The video really stresses that the Qiskit patterns hold up even at this scale.
Okay, let's follow the pattern. Step 1. Mapping the problem for 100 qubits. The circuit must be bigger.
Considerably. So to make this manageable, they write a Python function. Get Q4 and qubits en.
Ah, a reusable function that takes the number of qubits, n, as input. Smart.
Yep. Inside, it creates a quantum circuit n. Then, similar to the Bell state, it starts with a Hadamard on qubit 0.
Putting the first qubit into superposition.
Right. But then to entangle all the others, it uses a chain or ladder of CNOT gates.
Ladder, how does that work?
It applies a CNOT from qubit 0 to qubit 1, then a CNOT from qubit 1 to qubit 2, then 2 to 3, and so on.
All the way down the line, linking each one to the next.
Exactly. CNOT from I to I plus 1, all the way up to N2 and N1. This propagates the entanglement across the whole set.
That makes sense visually, like a domino effect.